Assalamu alaikum. My name is Sayyid Ali Murtaza and I am from Chemistry Department. Today the topic of my presentation is Atomic Absorption Spectroscopy. These are the contents in which we discuss the introduction, then sample atomization techniques, types of lamps, electrothermal atomization, specialized atomization techniques, instrumentation, spectrophotometers, interferences methods, analytical techniques, principles, working applications, software use. First of all, we study the what is atomic absorption spectroscopy. Atomic absorption spectroscopy detects elements in either liquid or solid samples through the application of characteristic wavelengths of electromagnetic radiation from a light source. Individual elements will absorb wavelengths differently, and these absorbances are measured against standards. History. Atomic emission spectroscopy was first used as an analytical technique, and the underlying principles were established in the second half of the 19th century by Robert Wilhelm Bunsen and Gustav Robert Kirchhoff, both professors at the University of Heidelberg, Germany. The modern form of atomic absorption spectroscopy was largely developed during the 1950s by a team of Australian chemists. They were led by Sir Alan Walsh at the Commonwealth Scientific and Industrial Research Organisation, Division of Chemical Physics in Melbourne, Australia. Sample atomization techniques. We first describe the two most common methods of sample atomization encountered in AAS and AFS. Same atomization and electrothermal atomization. We then turn to three specialized atomization procedures used in both types of spectroscopy. Flame atomization. In a flame atomizer, a solution of the sample is nebulized by a flow of gaseous oxidant mixed with the gaseous fuel and carried into a flame where atomization occurs, as shown in figure 9.1. A complex set of interconnected processes that occur in the flame. The first step is dissolution, in which the solvent evaporates to produce a finely divided solid molecular aerosol. The aerosol is then volatilized to form gaseous molecules. Dissociation of most of these molecules produces an atomic gas. Some of the atoms in the gas ionize to form cations and electrons. Other molecules and atoms are produced in the flame as a result of interactions of the fuel with the oxidant and with the various species in the sample. As indicated in figure, a fraction of the molecules, atoms and ions are also excited by the heat of the flame to yield atomic, ionic and molecular emission spectra. With so many complex processes occurring, it is not surprising that atomization is the most critical step in flame spectroscopy and the one that limits the precision of such methods. Because of the critical nature of the atomization step, it is important to understand the characteristics of flame and the variables that affect these characteristics. Here you can see the diagram of all these processes occurring during atomization. First analyte solution, then nebulization, spray, dissolution, solid or gas aerosol, volatilization, gaseous molecules, dissociation, reversible atoms, ionization, reversible atomic ions, then excitation, excited ions, excited atoms, excited molecules. Types of flames. Table lists the common fuels and oxidants used in flame spectroscopy and the approximate range of temperatures realized with each of these mixtures. Note that temperatures of 1700 degrees centigrade to 2400 degrees centigrade occur with the various fuels when air is the oxidant. At these temperatures, only easily decomposed samples are atomized, so oxygen or nitrous oxide must be used as the oxidant for more difficult to atomize samples, refractory samples. These oxidants produce temperatures of 2500 degrees centigrade to 3100 degrees centigrade with the common fuels. Flame structure. As shown in figure, important regions of a flame include the primary combustion zone, the interzonal region and the secondary combustion zone. The appearance and relative size of these regions vary considerably with the fuel to oxidant ratio, with the type of fuel and oxidant, and the type of burner. The primary combustion zone in a hydrocarbon flame is recognizable by its blue luminescence arising from the band emission of C2CH and other radicals. Thermal equilibrium is usually not achieved in this region, and it is therefore rarely used for flame spectroscopy. The interzonal area, which is relatively narrow in stoichiometric hydrocarbon flames, which may reach several centimeters in height in fuel-rich acetylene oxygen or acetylene nitrous oxide sources, because free radicals are prevalent in the interzonal region. It is the most widely used part of the flame for spectroscopy. In the secondary reaction zone, the products of the inner core are converted to stable molecular oxides that are then dispersed into the surroundings. A flame profile provides useful information about the processes that go on in different parts of the flame. It is a counter plot that reveals regions of the flame that have similar values for a variable of interest. Some of these variables include temperature, chemical composition, absorption, and radiant or fluorescence intensity. Here you can see the diagram, the regions in a flame. Temperature profiles. Figure shows a temperature profile of a typical flame for atomic spectroscopy. The maximum temperature is located in the flame about 2.5 cm above the primary combustion zone. It is important, particularly for emission methods, to focus the same part of the flame on the entrance slit for all calibrations and analytical measurements. Flame absorption profiles. Figure shows typical absorption profiles for three elements. Magnesium exhibits a maximum in absorbance at about the middle of the flame because of two opposing effects. The initial increase in absorbance as the distance from the base increases results from an increased number of magnesium atoms produced by the longer exposure to the heat of the flame. As the secondary combustion zone is approached, however, appreciable oxidation of the magnesium begins. This process eventually leads to a decrease in absorbance because the oxide particles formed do not absorb at the observation length. To achieve maximum analytical sensitivity, then the flame must be adjusted up and down with respect to the beam until the region of maximum absorbance is located. The behavior of silver, which is not easily oxidized, is quite different. As shown in figure, a continuous increase in the number of atoms, and thus the absorbance is observed from the base to the periphery of the flame. Here you can see the diagram of the flame absorption profiles for three elements. By contrast, chromium, which forms very stable oxides, shows a continuous decrease in absorbance beginning closer to the burner tip. This observation suggests that oxide formation predominates from the start. Flame atomizers. Flame atomizers are used for the atomic absorption, fluorescence, and emission spectroscopy. Figure is a diagram of a typical commercial laminar flow burner that uses a concentric tube nebulizer, similar to that shown in figure. The aerosol formed by the flow of oxidant is mixed with fuel and passes a series of baffles that remove all but the finest solution droplets. The baffles cause most of the sample to collect in the bottom of the mixing chamber, where it drains to a waste container. The aerosol, oxidant, and fuel are then burnt in a slotted burner to provide a 5 to 10 cm high flame. Laminar flow burners produce a relatively quiet flame and a long path length for maximizing absorption. For absorption, these properties tend to enhance sensitivity and reproducibility in AAS. The mixing chamber in this type of burner contains a potentially explosive mixture that can flash back if the flow rates are too low. Note that the laminar flow burner in figure is equipped with pressure relief vents for this reason. Other types of laminar flow burners and turbulent flow burners are available for atomic emission spectrometry and AFS. Here you can see the diagram of a laminar flow burner. Fuel and oxidant regulators. An important variable that requires close control in flame spectroscopy is the flow rate of both oxidant and fuel. It is desirable to be able to vary each other over a broad range so that optimal atomization conditions can be determined experimentally. Fuel and Oxidants are usually combined in approximately stoichiometric amounts for the determination of metals that form stable oxides. However, a flame that contains an excess of fuel is often desirable. Flow rates Flow rates are usually controlled by means of double diaphragm pressure regulators followed by the needle valves in the instrument housing. A lightweight conical or spherical bed is lifted by the glass by the gas. Its vertical position is determined by the FBW rate. Newer AAS instruments figure computer control over fuel and oxidant flows and flame ignition. Performance characteristics of flame atomizers. Flame atomization is the most reproducible of all liquid sample introduction methods that have been developed for AAS to date. The sampling of other atomization methods and thus the sensitivity, however, are markedly better than in flame atomization. There are two primary reasons for the low sampling of the flame. First, a large portion of the sample FBWS down the drain. Second, the residence time of individual atoms in the optical path in the flame is brief. Electrothermal atomization. Electrothermal atomizers, which first appeared on the market in the early 1970s, generally provide enhanced sensitivity because the entire sample is atomized in a short period and the average residence time of the atoms in the optical path is a second or more. Electrothermal atomizers are used for atomic absorption and atomic fluorescence measurements but have not been generally applied for direct production of emission spectra. After etching, the current is rapidly increased to several hundred amperes, which causes the temperature to rise to 2000 degrees centigrade to 3000 degrees centigrade. Atomization of the sample occurs in a period of few milliseconds to seconds. The absorption of the atomic vapor is then measured into the region immediately above the heated surface. Here you can see the diagram. The overall structure is explained here. Electrothermal atomizers. Figure is a cross-sectional view of a commercial electrothermal atomizer. In this device, atomization occurs in a cylindrical graphite tube that is open at both ends and that has a central hole for introduction of sample by means of a micropipette. The tube is about 5 cm long and has an internal diameter of somewhat less than 1 cm. Two inert gas streams are provided. The external stream prevents outside air from entering and incinerating the tube. The internal stream flows into the two ends of the tube and out of the central sample port. This stream not only excludes air but also serves to carry away vapors generated from the sample matrix during the first two heating stages. Figure illustrates the so-called Lvov platform, which is often used in the graphite furnaces. The platform is also made of graphite and is located beneath the sample entrance port. The sample is evaporated and etched on this platform. When the tube temperature is increased rapidly, however, atomization is delayed because the sample is no longer directly on the furnace wall. As a result, atomization occurs in an environment in which the temperature is not changing so rapidly, which improves the reproducibility of analytical signals. Figure which provides a continuously varying temperature profile as shown in figure. The transverse mode shown in figure gives a uniform temperature profile along the entire length of the tube. This arrangement provides optimum conditions for the formation of free atoms throughout the tube. Recombination of atoms to molecules, atom loss, and condensation on the cooler tube ends exhibited in the longitudinal mode are thus minimized in the transverse heating mode. Output signal. At a wavelength at which absorption occurs, the transducer output rises to a maximum after a few seconds of ignition, followed by a rapid decay back to zero as the atomization products escape into the surroundings. The change is rapid enough to require a moderately fast data acquisition system. Quantitative determinants are usually based on peak height, although peak area is also used. The series of 4 peaks on the right show the absorbance at the wavelength of a let peak as a function of time when a 2 mu L sample of canned orange juice was atomized. During drying and etching, 3 peaks appear that are probably due to the molecular evaporation products and particulate ignition products. The 3 peaks on the left are for LED standards used for calibration. The sample peak on the far right indicates a concentration of about 0.05 mu gram or milliliter of juice. Here you can see the diagram of figure 9.7. Performance characteristics of electrothermal atomizers. Electrothermal atomizers offer the advantage of unusually high sensitivity for small volumes of sample. Typically, the sample volumes between 0.5 and 10 mu L are used. Under these circumstances, absolute detection limits typically lie in the range of 102 gram of analyte. The relative precision of electrothermal methods is generally in the range of 5% to 10% compared with the 1% or better that can be expected for flame or plasma atomization. A final disadvantage is that the analytical range is relatively narrow, usually less than 2 orders of magnitude. As a result, electrothermal atomization is the method of choice only when flame or plasma atomization provides inadequate detection limits. Analysis of solids with electrothermal atomizers. In most methods based on electrothermal atomizers, samples are introduced as solutions. Several reports, however, have described the use of this type of atomizer for the direct analysis of solid samples. One way of performing such measurements is to weigh the finely ground sample into a graphite board and insert the board into the furnace manually. A second way is to prepare a slurry of the powder sample by ultrasonic agitation in an aqueous medium. The slurry is then pipetted into the furnace for atomization. Specialized atomization techniques. By far the most common sample introduction and atomization techniques for atomic absorption analysis are flames or electrothermal vaporizers. Several other atomization methods are used occasionally. However, three of these are described briefly in this section. Glow discharge atomization. As described in section 8C2, a glow discharge device produces an atomized vapor that can be swept into a cell for absorption measurements. Figure shows a glow discharge cell that can be used as an accessory to most flame atomic absorption spectrometers. It consists of a cylindrical cell about 17 cm long with a circular hole about 2 cm in diameter cut near the middle of the cylinder. An O-ring surrounds the hole. The organ is ionized by a current between an anode supporting the nozzles and the sample, which act as a cathode. As a result of sputtering, 6 craters quickly form on the sample surfaces as shown in figure. The splittered atoms are drawn by a vacuum to the axis of the cell where they absorb radiation from the spectrometer source. For this technique to be applicable, the sample must be an electrical conductor or must be made into a pellet with a powder conductor such as so finely ground graphite or copper. Solution samples have also been analyzed by a deposition on a graphite, aluminum or copper cathode. Detection limits with this type of device are reported to be in the low parts per million range for solid samples. Cold vapor atomization. The cold vapor technique is an atomization method applicable only to the determination of mercury because it is the only metallic element that has an appreciable vapor pressure at ambient temperature. The determination of mercury in various types of samples is of vital importance currently because the toxicity of organic mercury compounds and their widespread distribution in the environment. One popular method for this determination is cold vaporization, followed by atomic absorption spectrophotometry. The elemental mercury is then swept into a long pass absorption tube similar to one shown in figure by bubbling a stream of inert gas through the reaction mixture. Here you can see the diagram of hydride generation and atomization systems for AAS. Instrumentation for atomic absorption spectroscopy are similar in general design so that shown in figure and consist of a radiation source, a sample holder, a wavelength selector, and a detector and a signal processor and readout. 9. The sample holder in atomic absorption instruments is the atomizer cell that contains the gaseous atomized sample. Radiation sources. Atomic absorption methods are potentially highly specific because atomic absorption lines are remarkably narrow and because electronic transition energies are unique for each element. On the other hand, narrow line widths create a problem that does not normally occur in molecular absorption spectroscopy. In section we show that a relationship between the analytical signal and concentration, that is for Beer's law, as given by equation. To be obeyed requires a narrow source bandwidth relative to the width of an absorption line or a band. Even good quality monochromators, however, have effective bandwidths significantly greater than the width of atomic absorption lines. As a result, non-linear calibration curves are inevitable when atomic absorbance measurements are made with an ordinary spectrophotometer equipped with continuum radiation source. Furthermore, the slopes of calibration curves obtained in these experiments are small because only a small fraction of the radiation from the monochromator slit is absorbed by the sample. The result is poor sensitivity. Clouded this issue, and such instruments are beginning to compete with traditional spectrometers equipped with line sources. Here you can see the diagram of absorption of a resonance line by atoms. Hollow-cathode lamps. The most common source for atomic absorption measurements is the hollow-cathode lamp, such as one shown in figure. This type of lamp consists of a tungsten anode and a cylindrical cathode sealed in a glass tube filled with neon or argon at a pressure of 1 to 5 torr. The cathode is constructed of the metal whose spectrum is desired or serves to support a layer of that metal. Ionization of the inert gas occurs when a potential difference on the order of 300 volt is applied across the electrodes, which generates a current of about 5 to 15 milliamperes. As ions electrons migrate to the electrodes, if the voltage is sufficiently large, the gaseous cations acquire enough kinetic energy to dislodge some of the metal atoms from the cathode surface and produce an atomic cloud in a process called sputtering. Here you can see the schematic cross section of a hollow cathode lamp diagram. Electrode-less discharge lamps. Electrode-less discharge lamps are useful sources of atomic line spectra and provide radiant intensities usually 1 to 2 orders of magnitude greater than hollow cathode lamps. 13. A typical lamp is constructed from a sealed quartz tube containing a few torr of an inert gas such as argon and a small quantity of the metal whose spectrum is of interest. Ionization of the argon occurs to give ions that are accelerated by the high frequency component of the field until they gain sufficient energy to excite the atoms of the metal whose spectrum is sought. Here you can see the diagram of figure 9/12 is a schematic of a commercial EDL which is powered by 27 MHz radio frequency source. Source modulation. In the typical atomic absorption instrument, it is necessary to eliminate interferences caused by emission of radiation by the flame. The emitted radiation at wavelengths outside of monochromator band pass is of course removed by the monochromator. However, to eliminate the effects of the flame emission, it is necessary to modulate the output of the source so that its intensity fluctuates at a constant frequency. The detector then receives two types signal and alternating one from the source and continuous one from the flame. These signals are converted to a corresponding types of electrical response. A simple high pass RC filter can be used to remove the unmodulated DC signal and pass the AC signal for amplification. Spectrophotometers. Instruments for atomic absorption measurements are offered by numerous manufacturers. Both single and double beam designs are available. The range of sophistication and cost is substantial. Single beam instruments. A single beam instrument such as that shown in figure consists of several hollow cathode sources, a chopper or a pulsed power supply, an atomizer and a simple grating spectrophotometer with a photomultiplier transducer. In use, the dark current is first nulled with a shutter in front of the transducer. The 100% transmittance adjustment is then made while a blank is aspirated into the flame or ignited in an electrothermal atomizer. Here you can see the diagram of single beam instruments. Double beam instruments. Figure is the Schematic of a typical double beam in time instrument. The beam from the hollow cathode source is split by a mirrored chopper, one half passing through the flame and the other half around it. The two beams are then recombined by a half silvered mirror and then passed to a grating monochromator. A photomultiplier tube serves as the transducer. The output from the latter is the input to a log, which is typically a digital meter or a computer. Here you can see the diagram of a double beam instrument. Interferences in atomic absorption spectroscopy. Interferences are of two types are encountered in atomic absorption methods. Spectral interferences arise when the absorption or emission of an interfering species either overlaps or lies so close to the analyte absorption or emission that the monochromator cannot dissolve them. Chemical interferences result from the various chemical processes occurring during atomization that alter the absorption characteristics of the analyte. Spectral interferences. Because the emission lines of hollow cathode sources are very narrow, interference because of overlapping lines is therefore such an interference to occur. The separation between the two lines would have to be less than about 0.1 angstrom. For example, a vanadium line at 3082.11 angstrom interferences is the determination of aluminum based on its absorption line at 3082.15. The interference is easily avoided, however, by using the aluminum line at 3092 instead. The spectral interferences also result from the presence of combustion products that exhibit broadband absorption or particulate products that scatter radiation. Both reduce the power of the transmitted beam and lead to a positive analytical errors. When the source of these products is the fuel and oxidant mixture alone, the analytical data can be corrected by making absorption measurements while a blank is aspirated into the flame. Note that this correction must be used with the both double beam and single beam instruments because the reference beam of a double beam instrument does not pass through the flame. A much more troublesome problem occurs when the source of absorption or scattering originates in the sample matrix. In this instance, the power of transmitted beam P is reduced by the matrix components, but the incident beam power PO is not. The result is a positive error in absorbance and thus concentration. Spectral interference because of scattering byproducts of atomization is most often encountered when concentrated solutions containing elements such as TiZr and W, which form refractory oxides, are aspirated into the flame. Metal oxide particles with diameters greater than the wavelength of light appear to be formed, and scattering of the incident beam results. Interference caused by scattering may also be a problem when the sample contains organic species or when organic solvents are used to dissolve the sample. The added substance is sometimes called a radiation buffer. The method of standard additions can also be used advantageously in some cases. The two-line correction method. The two-line correction procedure uses a second line from the source as a reference. The wavelength of the reference line should be as close as possible to that of the analyte, but must not be absorbed by the analyte. If these conditions are met, it is assumed that any decrease in power of the reference line from the observed during calibration arises from the absorption or scattering by the matrix products of the sample. The continuous source correction method. Figure illustrates a second method for the background correction that is widely used. In this technique, a deuterium lamp provides a source of continuum radiation throughout the ultraviolet region. Here you can see the diagram of schematic of continuum source background correcting system. Note that the chopper can be eliminated by alternating pulsing each lamp. Unfortunately, although most instrument manufacturers offer continuous source background correction systems, that performance of these devices is often less than the ideal, which leads to undercorrection in some systems and overcorrection in others. Background correction based on the Zeeman effect. When an atomic vapor is exposed to a strong magnetic field, a splitting of electronic energy levels of the atoms takes place that leads to a formation of the several absorption lines for each electronic transition. These lines are separated from one another by about 0.1 nanometer, with the sum of the absorbances for the lines being exactly equal to that of the original line from which they are formed. This phenomenon, which is termed as Zeeman effect. The center line, which is at the original wavelength, has an absorbance that is twice that of each lines For more complex transitions, further splitting of the P and S lines occurs. A second type of Zeeman effect instrument has been designed in which a magnet surrounds the hollow cathode source. Here it is the emission spectrum of the source that is split rather than the absorption spectrum of the sample. This instrument configuration provides an analogous correction. To date, most instruments are of the types illustrated in figure. Here you background correction based on the source self renewal. A remarkably simple means of background correction offers most of the advantages of a Zeeman effect instrument. The net effect, which is used to produce a line that has a minimum in its center, which corresponds exactly in the wavelength to that of absorption line. Atomic absorption analytical techniques. Sample preparation. A disadvantage of flame spectroscopic methods in the requirements that the sample can be introduced into the excitation source in the form of a solution, most commonly an aqueous one. Unfortunately, many materials of interest such as soils, animal tissues, plants, petroleum products, and minerals are not directly soluble in common solvents. One of the advantages of electrothermal atomization is that some materials that can be atomized directly, thus avoiding in the solution step. For example, liquid samples such as blood, petroleum products, and the organic solvents can be pipetted directly into the furnace for etching and atomization. Calibration is, however, usually difficult. Required standards that approximate the sample in composition. Sample introduction by flow injection. We describe the methods and instrumentation for flow injections in analysis. FIA methodology serves as an excellent means of introducing samples into a flame atomic absorption spectrometer. From any perspective, the peristaltic pump and valve arrangements of FIA described in Chapter 33 are a convenient means to sample analyze solutions reproducibly and efficiently, especially when it is important to conserve sample. Organic solvents. Early in the development of atomic absorption spectroscopy, it was recognized that enhanced absorbances could be obtained if the solutions contained low molecular mass alcohols, esters, or ketones. The effect of organic solvents is largely attributable to increased nebulizer efficiency. The lower surface tension of such solutions leads to a smaller drop sizes and a resulting increase in the amount of sample that reaches the flame. Unfortunately, however, the linear mixture produces lower flame temperatures and an increased potential for chemical interferences. Principle of atomic absorption spectroscopy. The basic principle of atomic absorption spectroscopy can be expressed as follows. Firstly, all atoms or ions can absorb light at specific unique wavelengths. When a sample containing copper and nickel, for example, is exposed to light at the characteristic wavelength of copper, then only the copper atoms or ions will absorb this light. The amount of light absorbed at this wavelength is directly proportional to the concentration of the absorbing ions or atoms. The electrons within an atom exist at various energy levels. When the atom is exposed to its own unique wavelength, it can absorb the energy and electrons move from a ground state to excited state. The radiant energy absorbed by the electrons is directly related to the transition that occurs during the process. Furthermore, since the electronic structure of every element is unique, the radiation absorbed represents a unique property of each individual element and can be measured. An atomic absorption spectrometer uses these basic principles and applies them in practical quantitative analysis. A typical atomic absorption spectrometer consists of four main components. Here you can see the diagram, the principle of working. Atomic absorption spectroscopy detects elements in either liquid or solid samples through the application of characteristic wavelength of electromagnetic radiation from a light source. Individual elements will absorb wavelengths differently, and these absorbances are measured against standards. In effect, AAS takes advantage of the different radiation wavelengths that are absorbed by different atoms. Applications. As we have stated, atomic absorption spectroscopy is utilized in a wide variety of industries and areas of scientific study. Some of more applications for this technique are listed below. Forensics. Atomic absorption spectroscopy has been utilized in the study of forensic sciences for many years. Using the technology, forensic scientists can perform in-depth analysis of blood sample, brain and muscle tissue, and gunshot powder residue. This technology has vastly improved the accuracy of toxicology reports in cases of metal poisoning. Common causes of metal poisoning, such as mercury and lead, are easily detectable using this technique and can be identified even in trace amounts. Agriculture. Atomic absorption spectroscopy is frequently utilized in agriculture and the study of environmental sciences. Atomic absorption spectroscopy, as well as atomic fluorescence spectroscopy, which analyzes the light emitted from a sample rather than the light absorbed, are frequently used in various fields of agricultural study. Typically, they are used to identify and analyze the presence of potentially harmful elements in the environment. One common use for these methods is the analysis of soil samples and the effect the quality of soil will have on the overall rate of food production in a certain area. Software use. Spectra software, Spectra CFR, AAS software, Agilent. The FPLIMS software is designed for centralized test handling and manages all data collected by atomic absorption spectrometers. Thank you.